This higher chemistry video is going to look at intermolecular forces, and it's going to relate physical properties of compounds to the intermolecular forces in terms of boiling point, viscosity and solubility. These are the SQA learning outcomes we're going to look at today. To summarize it in one short sentence, we're going to look at how boiling point, viscosity and solubility can be affected by intermolecular forces. The strength of London dispersion forces is related to the number of electrons within an atom or molecule. I'm going to use the first four alkanes as an example. We have methane, ethane, propane and butane. As we go from left to right, they've got more atoms in their molecule, therefore more electrons. The more electrons that are present in the molecule, the stronger the London dispersion forces between the molecules, therefore the higher the boiling point. So we can see that methane has the lowest boiling point, and the boiling points increase to -1 degrees by the time we reach butane. So we know the melting and boiling point of a substance depends on the strength of the intermolecular forces between its molecules. To predict the relative melting or boiling point of a substance, two factors need to be considered: the total number of electrons in the molecule, which we did in the last slide. The next slide we will look at the type of van der Waals bonding present between the molecules in terms of, is it hydrogen bonds, permanent dipole interactions, or London dispersion forces. Here we have the diagrams for a structural formula for three different molecules. We have for propane, methoxymethane and ethanol. There are two questions I want you to answer on a pen and paper. The first one is, what types of van der Waals forces will be present between each of the molecules? And secondly, which will have the lowest and highest boiling point? So pause it, have a go, and then see if you're correct. So the first question asked, what types of van der Waals forces are present between the molecules? Well, each of the molecules contains atoms and therefore electrons that can move around, so they're all going to have London dispersion forces between their molecules. If we look at the number of electrons present in each molecule, they each have 26 electrons present. So we can say that each of the compounds has the same number of electrons, so would be expected to have London dispersion forces of similar strengths. If we look at propane, we can see that propane is a non-polar molecule. It's symmetrical, it's a hydrocarbon, there's no permanent dipole, so the only significant force between propane molecules will be London dispersion forces, the weakest intermolecular force. If we look at methoxymethane, we can see we've got a polar carbon-oxygen bond. If we look at the electronegativities, oxygen will have a higher electronegativity value and give you a partial negative charge above that oxygen. Looking at this carbon-hydrogen bond, carbon is a slightly higher electronegativity value than hydrogen, so we'll get a positive charge at this hydrogen. So each of these molecules has a permanent dipole. So what that means is that we can have permanent dipole interactions between methoxymethane molecules as well as London dispersion forces. Finally, looking at ethanol, what should jump out are these hydroxyl groups at the ends. These very polar OH bonds allow the two ethanol molecules to have the intermolecular force we know as hydrogen bonding between them, which is the strongest intermolecular force. So if we relate this to the boiling point, well, propane has the weakest forces between the molecules, London dispersion forces, so it will have the lowest boiling point at -44 degrees Celsius. Methoxymethane will have the next highest one because the permanent dipole interactions are stronger at -22. But because ethanol has hydrogen bonding between its molecules, it will have the highest boiling point with +78 degrees Celsius. So we can say that rather than being different in terms of their electrons, the differences in their boiling points are due to other types of van der Waals forces present. This is the next question for you to try, so it's worth 2 marks. So pause the video, write down the answer, and then check the marking scheme that's going to come up. So the question is asking, what's the strongest type of intermolecular force present in this molecule? Now we know the strongest type of intermolecular force is hydrogen bonding, but that's not going to be present between molecules of hydrogen sulfide because we don't have oxygen, nitrogen or fluorine joined to hydrogen. However, we do have a permanent dipole here between sulfur and hydrogen. Sulfur has a higher electronegativity, so it will have a negative charge given positive charges at the hydrogens. So we can say that hydrogen sulfide has permanent-dipole interactions between its molecules. So that would get you 1 mark. The one that people often forget to do is saying how the force arises. So you've got to say how you get permanent-dipole interactions. So some mention the dipole is needed to be required. You need to show the charges or draw the electronegativities on and mention how these permanent dipoles can cause interactions between molecules. So that's the 2nd mark as well. One thing to note that if you're in an exam, if you put the wrong force by mistake, such as LDFs, you wouldn't get penalised twice for it. So if you put London dispersion forces and correctly named statements about induced temporary dipoles and so on, you'd maybe still get 1 mark out of 2. This question is worth 3 marks and has the words in bold here explained fully. So a lot of details required to get all 3 marks. So pause the video, have a go at it, and then we'll see if you've bagged all 3 marks or not. So the first part is explain why the boiling point of hydrogen fluoride is much higher than that of fluorine. So what that tells us is that the intermolecular forces between hydrogen fluoride are stronger and require more energy to break than between fluorine molecules. So that gets you the 1st mark. Do not put the hydrogen fluoride as a stronger bond than fluorine, or that covalent bonds are broken. Those are not broken when we boil molecules. It's the intermolecular forces between the molecules that are broken. Looking at the intermolecular forces involved, well, we can see that hydrogen is joined to fluorine, so that means the molecules can form hydrogen bonds with each other. And to say how they arise, like how hydrogen bonds are formed, you need to mention that the more electronegative fluorine will cause a permanent dipole to be formed. You can draw the electronegativities of the charges on, and that will get you the 2nd mark. We'll need to talk about the forces between the fluorine molecules too. Fluorine is a non-polar molecule, so the only force between the fluorine molecules will be London dispersion forces, and some sort of description about how they arise by temporary dipole induced dipole attraction, movement of electrons, will get you the 3rd mark. We're now going to look at viscosity, or the thickness of a liquid, and there's 2 things that can affect the viscosity of a liquid in terms of intermolecular forces. One is the strength of the intermolecular forces, and 2 is the type of forces such as hydrogen bonding. So that's what we're going to look at next. You will probably have come across viscosity before when studying fractional distillation. A reminder what fractional distillation is: it's a process in which the hydrocarbons or alkanes in crude oil can be separated using their different boiling points. So we've got 4 fractions here: petrol, diesel, lubricating oil and bitumen. And as we go down these fractions, the number of carbon atoms increases. The hydrocarbon gets longer. So the number of carbons and hydrogens increase, and therefore the boiling point increases. In addition to that, the viscosity will increase. So petrol is very runny, and your oils and tars like lubricating oil and bitumen get a lot thicker. And the reason for this is as the number of carbon atoms increases and hydrogen atoms increases, the amount of electrons increases in the molecule, and the strength of the London dispersion forces increase in the molecule. So this increases the boiling point, and because you've got more attractions between the hydrocarbon molecules, the viscosity will increase as well. The liquids will get thicker. So to summarize, as the total number of electrons in the molecule increases, the viscosity increases. Okay, we're going to make a prediction here. So we've got 4 different test tubes with 4 different liquids of different viscosities or thicknesses, and we're going to simultaneously drop a ball bearing into each one. So looking at the different solutions we've got here and their structural formula, I want to predict what order will the balls reach the bottom when dropped, from fastest to slowest. So pause the video, have a guess, and then see if you're correct. Okay, so here's what happens when we drop the ball bearings in. In pentane, the ball reaches the bottom first, then we got methanol, then we got water, and last but not least, glycerol. So we can say that pentane has the least viscous liquid and glycerol is the most viscous. So the reason for this is that pentane has non-polar molecules present in it. You can see that they're symmetrical, they're hydrocarbons, and the only forces between pentane molecules will be London dispersion forces. The next liquid in terms of viscosity would be methanol, and you can see this can form hydrogen bonds because we've got one hydroxyl group present in it. Water is a bit thicker though because it's got two OH groups, so it can form two hydrogen bonds between its molecules, unlike methanol which has got one. And the reason that glycerol is the most viscous liquid is that it has three hydroxyl groups. That means that molecule can form three hydrogen bonds with other glycerol molecules. So we can see that in addition to looking at the electrons present in the molecules, if we look at the functional groups such as OH groups or NH groups in terms of hydrogen bonding, that will have an effect on the viscosity. This will also have an effect on the boiling point as well. You can see that the more OHs that are present in the molecules, the higher the boiling point. And if you have just London dispersion forces between the molecules like pentane, it will have the lowest boiling point. This is a pond skater skating or walking across water. The hydrogen bonds between the water molecules give the water a sort of viscosity or stickiness that stops the pond skater falling through. Okay, we've looked at boiling points and viscosity, and now we're going to look at solubility. So what we're going to look at now is how intermolecular forces can determine whether or not a substance will dissolve in a solvent or not. Here is a solubility experiment we're going to look at. So we've got two different solvents in this experiment. We've got water, which we term a polar solvent due to the fact we've got polar water molecules present. And in hexane, we've got non-polar hexane molecules, so we call that a non-polar solvent. Our solutes, which we're going to try and dissolve into these solvents, are glycerol. The hydroxyl groups make glycerol a polar molecule. We have iodine, which is a non-polar molecule, and we have an ionic compound, which is sodium chloride. So this is the data from the experiment in terms of solubility. So I want you to pause it and come up with a conclusion from this experiment. So what you can see is that polar molecules dissolve in polar solvents. So we can see that polar glycerol dissolves in polar water, but not non-polar hexane. Non-polar iodine will dissolve in non-polar hexane, but not in polar water. And if we look at sodium chloride, it will dissolve in the polar water, but not the non-polar hexane. So we can conclude that ionic compounds such as sodium chloride and polar molecular compounds such as glycerol tend to be soluble in polar solvents such as water and insoluble in non-polar solvents such as hexane. Conversely, non-polar molecular substances such as iodine tend to be soluble in non-polar solvents such as hexane and insoluble in polar solvents such as water. So we can really say that like dissolves like, i.e. polar dissolves in polar, non-polar dissolves in non-polar. Whenever you put oil and water together in a beaker and shake it, you'll get two layers. Oil and water don't mix. We say the liquids are immiscible. The same will occur with hexane, which is non-polar, and water, which is polar. So we say that hexane and water are also immiscible. Hexane will only dissolve non-polar substances in it as well. So that includes non-polar alkanes, which are present in crude oil, fats, oils. Non-polar molecules such as iodine and bromine will also dissolve in non-polar hexane as well. Polar water, however, will dissolve ionic compounds, polar molecules such as ammonia, and fairly small molecules with hydroxyl groups such as alcohols will also dissolve in it as well. To predict the solubility of a compound, say in water, the presence in the molecules of OH or NH bonds, which implies hydrogen bonding, needs to be considered. So generally, if the compound can form hydrogen bonds, there's a good chance it will dissolve in water. So for instance, if we look, ethanol and amino acids are polar substances and will dissolve in polar water, but will not dissolve in non-polar hexane. So you can generally say that if the compound has molecules that can form hydrogen bonds, they tend to be capable of dissolving in water. Now that's not always the case. If there's a big non-polar part to it, it may not, but generally that's a rule we can use. This question is worth 2 marks. You need to look at the full structural formula of this chemical, procyanidin B2 and explain fully why it is water soluble. So pause the video and see how you get on. If you look at the structural formula, what should jump out at you are the presence of these hydroxyl groups all around the outside of the molecule. This tells us that the molecule is polar due to these hydroxyl groups. So that would get you the first mark. The molecule is polar due to its hydroxyl groups, and it can form hydrogen bonds. That's another point you could make. If the molecule is polar, that means it will dissolve in a polar solvent such as water, or can form hydrogen bonds with water, and that would get you the second mark, an explanation which links solubility of the molecule to the polarity of water and the fact that it can hydrogen bond to the water. As well as looking at the functional groups present in the molecules, we need to consider the shape and the spatial arrangement of the polar covalent bonds within the molecule to determine its solubility in water or hexane. One of these will dissolve in water, one of these will dissolve in hexane. Have a think about which one it will be before we continue. So if we look at trichloromethane first, and we look at the electronegativity values and the charges, we can see we get this occurring, in which we have a permanent dipole in the molecule. So we have a polar molecule. Polar molecules will dissolve in polar solvents such as water, so this molecule will dissolve in water. If we look at tetrachloromethane, we can see that it is a symmetrical molecule. Therefore, it will be nonpolar. Therefore, it will dissolve in nonpolar hexane. So here is a little chemistry joke to lighten the mood here. So why is this bear dissolving in the water? The punchline to this is because it's polar. So polar substances will dissolve in water. Okay, so we're going to finish off in a 3-mark question. And what this question is basically asking is, why is this molecule, trichloromethane, more soluble in water than this molecule, tetrachloromethane? And we need to name the intermolecular forces involved. So the first thing to do is look at the shapes of the molecules. Also, the electronegativity values and the charges will help too. If we do this for trichloromethane, you can see we've got a permanent dipole here. So this is a polar molecule. If we look at tetrachloromethane, this is a symmetrical molecule, so it will be nonpolar. So the first mark is for stating that trichloromethane is polar and tetrachloromethane is nonpolar. In terms of naming the intermolecular forces involved, we can see we've got a permanent dipole present in this molecule, so it will have permanent dipole interactions between its molecules. It won't have hydrogen bonds between its molecules because we don't have OH groups or NH groups within the molecule. This one, being nonpolar, will only have London dispersion forces between its molecules. So that's the second mark, identifying that trichloromethane has permanent dipole interactions, and tetrachloromethane has London dispersion forces between its molecules. Now we need to relate this to the solubility. Because this is a polar molecule, it will dissolve in water, which is a polar solvent. So some kind of statement relating this, such as water is polar, water has permanent dipole attractions, or water is a good solvent for polar molecules, will get you the 3rd mark. So I hope this video will help you relate the properties of substances such as boiling points, viscosity and solubility to the intermolecular forces involved.